What is up? I've never actually done this before. I've given reviews, I think, like since I first started grad school, but I've never actually done like a screen recording before. So I'm really hoping that my voice at least is pretty audible during this. If you watch this and you have questions on like a particular moment because you can't really understand what I'm saying, please just reach out to me and I'll try to clarify it. But I'm going to do my best to actually enunciate all my words so that we don't run into that issue. But yeah, like I said, I've never done this before, so hopefully it goes out well. I think I'm going to make multiple ones of these videos. This one is just going to be like something that, in my opinion, you guys should know. Actually, multiple things, not just one thing, but multiple things that I hope you guys remember from Orgo 1 and general chemistry. That in my opinion are really useful and used a lot in Orgo, both Orgo 1 and Orgo 2. And so I'm going to go ahead and get started because I don't want this video to be too long. So the very first, oh fuck, I got an eraser on, god damn it. Alright, better. So the very first thing that I want you guys to be like very, very, very proficient at, okay, is the octet rule, okay? And we should be able to fly through this, okay? Not really a whole lot to talk about the octet rule. Basically, with very few exceptions, okay, every atom in a molecule, okay, every atom in a molecule needs 8 total electrons, alright, total electrons, and they can come from bonds or lone pairs, okay. Obviously a bond is going to count as 2 electrons. A lone pair is also going to count as 2 electrons, okay? And again, there are some exceptions to this. I will tell you what those exceptions are, but for example, if I draw a molecule of methane, okay, right, and we look at carbon, carbon would be following the octet rule because it has 1 bond, 2 bonds, 3 bonds, 4 bonds, so 2, 4, 6, 8 electrons, okay? Hydrogen, you might notice, is breaking the octet rule. I'll talk about that in a little bit. Hydrogen is one of the exceptions. Hydrogen will not follow the octet rule, and I'll get to why in a little bit. But again, right, if I'm drawing another molecule, right, maybe I can draw a molecule of 1, 2, 3 propanol, right there, okay? And you can see, I'll actually draw the bond to hydrogen, so it's a little bit easier to see. Okay. But again, the oxygen here is following the octet rule, right? I have 1 bond, lone pair, lone pair. So again, that oxygen has 2, 4, 6, 8. Okay, if you draw in the implied hydrogens on carbon, you'll see that the carbons are all following the octet rule as well. For example, this one has a hydrogen, and a hydrogen. So that carbon has 4 bonds. Right, the carbon-carbon bond right there, and then the 3 carbon hydrogens. So that carbon, again, is following the octet rule, okay? So, don't want to spend too much time on this. I'm just going to write really quickly down the ones that don't follow the octet rule. So, obviously, hydrogen does not follow the octet rule, okay? So hydrogen breaks, actually, I'll organize this a little bit better. So I'll say, oh, no, not black. Alright, so octet rule breakers, right? So hydrogen breaks the octet rule, and the reason hydrogen breaks the octet rule is because if you actually look on the periodic table, hydrogen only has one singular 1s orbital, and an orbital can only hold 2 electrons. So hydrogen is only ever going to have a maximum of 2 electrons. That one's pretty easy. Another one that you guys might remember is all of the group 3 atoms. So it's going to be like aluminum, boron. Those are the only ones that I'm going to write down. There are other atoms in the 3rd group of the periodic table, but in organic chemistry you guys aren't really ever going to encounter them, so that would be something like germanium. We don't really use them in organic chemistry. But aluminum and boron, these guys are actually going to be satisfied with only having 6 electrons. And for organic chemistry, these are the only 2 exceptions that I actually want you guys to worry about. And I already told you why hydrogen breaks the rule. Hydrogen breaks the rule because it only has a 1s orbital. Aluminum and boron are going to break the rule for a formal charge reason, and I'm going to get to that reason in a little bit. Okay. And I just realized there's totally another set of rule breakers, so my bad, there's actually 3 of them. So these two rule breakers right here, they break the rule because they have less, or they can have less than an octet. The third class of rule breakers, they break the rule because they can have more. So you can have an expanded octet. You can have an expanded octet with any element. Alright, so any element that is heavier than silicon. Well, heavier or equal to silicon. So if you look at the periodic table, silicon is directly below carbon, so silicon and then anything that has a higher atomic number than silicon technically can have an expanded octet, which means that it can have 10 electrons, or sometimes it can have as many as 12 electrons, and there are some organic compounds that you'll work with, or at least that you'll see in your textbook, that have expanded octets of 10 or 12 electrons. But that's really all there is to know about the octet rule. Please make sure you understand that these are the only exceptions to the octet rule. Hydrogen has 2, aluminum and boron have 6, and things like silicon and phosphorus and stuff like that, they can have more than 8. They can have 10, they can have 12. It just depends on sort of what chemistry you're actually doing with them. Alright, so that's pretty much all I have to say about the octet rule. So the next one that I'm going to talk about, the next thing that I want to talk to you guys about is formal charge. Okay, I want all of you to be extremely rapid at assigning formal charge to every single atom in a molecule. Alright, and the other reason I want to talk about formal charge right now is because it'll help explain why aluminum and boron follow, or actually don't follow the octet rule. So, first of all, so formal charge is an estimation. And I want you guys to understand this. It is just an estimation. It's an approximation. It is not the reality. That's why it's called formal charge and not just charge, right? So it's an estimation of the charge on an atom in a molecule. On an atom, okie dokie, in a molecule. Okay. Okay, so if it's an estimation, that must mean that we take some simplifying assumptions. So what are those simplifying assumptions? So what formal charge, so we assume, and this is why it's an estimation, because this is not always a correct assumption, but we assume that in a covalent bond, electrons are perfectly shared. Okay? And we know that this is not the case, right? Because you guys know of this thing called electronegativity. So if I have something like water, right? We know, right? So we have these 2 bonds. We have a bond right here and a bond right there. We know that the 2 electrons that are in those bonds are not perfectly spaced between the oxygen and the hydrogen. You guys know that both of those electrons, if we were to really draw that, sort of more accurately, right, those electrons would be much closer to the oxygen than they are to the hydrogen, right? This would not be, right, this would be sort of a correct version of that. And an incorrect version of that would be to actually assume that everything is sort of equally spaced, okay? But when we're doing formal charge, we're going to ignore electronegativities, and we're just going to assume that in a covalent bond, electrons are exactly equidistant from one another. Or sorry, electrons are equidistant from the 2 nuclei. Alright. So, once we know that, all we have to realize is that the number of electrons that an atom wants is just equal to its group number. All right. And when I say group number, so I want you to ignore the transition metals. So the transition metals / the D block of the periodic table. So if you're looking at the periodic table, what I mean by this little ignore it part is that, like, boron and aluminum, even though it's technically group 13, don't count the transition metals, which are 10 groups wide. So that would actually be group 3, right? Carbon and silicon would be group 4. Nitrogen and phosphorus would be 5. Oxygen and sulfur would be 6. Yada yada yada. Fluorine, chlorine, bromine, iodine would be 7. Okay, whatever. Beryllium would be group 2. And of course, hydrogen would be group 1. Okay? So, if you know how many electrons an atom wants, okay, in order for it to be stable, then what you can do in a molecule is you can count how many electrons it has. Right, so I'm going to draw a molecule of diethyl ether. Okay. Alright, so let's do the formal charge of the oxygen. Alright, so if I'm counting the number of electrons that this oxygen has, the lone pairs are probably the easiest to count. So it has 1, 2 right there, 3, 4 right there. And if you remember, in formal charge, we're going to assume that every bond is perfectly equally, the electrons in a bond are perfectly equally shared, which means that even though there are 2 electrons in this bond, according to the octet rule, from a formal charge perspective, the oxygen only gets 1 of the electrons, and the carbon gets another 1 of the electrons. Alright, so hopefully that makes sense. And what that means is that in this bond, there is 1 electron for oxygen. And in this bond right here, there is 1 electron for oxygen. The other electron, according to formal charge, is for the carbon. Alright, so by the way, that's the main difference between formal charge and the octet rule. So, you might have, asked yourself, okay, Brian, you just 5 minutes ago said that every single atom wants 8 electrons, and now you're saying that the number of electrons it wants is based on its group number. It wants 8 total electrons, okay? Meaning that, a bond counts as both of the electrons, right? It basically wants to be surrounded by 8 electrons, but formal charge is only, okay, so only count a bond. So in formal charge, you only count a bond as 1 electron. And again, the reason you only count it as 1 electron is because formal charge is going to assume that when you have a bond between atom A and atom B, which is the reality, is that a bond is made up of 2 electrons, right? Formal charge means that atom A gets that electron and atom B gets that electron, and that's it, okay? So with all of that said, I want you guys to get really, really good, okay, at doing a bunch of these formal charges, okay? So I'll do maybe something like this. Hold on. Alright, so I'm going to draw a molecule that looks like this, alright? And I'm going to go through it with you, but one thing that I want you to do, again, is I want you guys to be really, really good at looking at a molecule like this and very rapidly determining what the formal charge of the atoms in that molecule are, alright? So let's actually go over this really quickly, right? So first of all, if you look at where nitrogen is on the periodic table, nitrogen is in group 5. So nitrogen wants 5 electrons. Oxygen is in group 6. Oxygen wants 6 electrons. All right. So let's go ahead and do this really quickly. Nitrogen has 1, 2, 3, 4, 5, 6. This nitrogen has 6 electrons, but it only wants 5. Therefore, this nitrogen is going to be formally negative. All right, let's do this oxygen up top. This oxygen up top has 1, 2, 3, 4, 5, 6. Notice that because it was a double bond which normally has 4 electrons, formal charge indicates that that double bond is perfectly shared, so the oxygen gets 2 of the 4, the carbon gets 2 of the 4. Again, the other way to think about it, like I said, is that one bond is 1 electron. So therefore, a double bond would be 2 electrons, a triple bond would be 3 electrons. All right, so anyway, oxygen 1,6, we just realized that that oxygen has 6, which means that that oxygen is formally neutral. All right, let's do the oxygen on the right. So that one would have 1, 2, 3, 4, 5, 6, 7. It has 7 electrons, it wants 6. Therefore, it has an extra one, and that means that this oxygen is formally negative. If we do this oxygen down here, it has 1, 2, 3, 4, 5. So it has 5, it actually wants 6, so it's missing an electron. That means that this oxygen down here is formally positive. All right. So these would be the assignments of all of the formal charges in this molecule. Okay. And then a final note that I'm going to put on formal charge, okay, is you can actually see why something like boron and aluminum don't follow the octet rule because of formal charge considerations. So if I draw a molecule of AlH3 and I asked you, is this molecule positive, negative, or neutral? Okay, you could just do the formal charge on this, right? So if I do the formal charge on hydrogen, right, let's do the formal charge on each hydrogen. So this hydrogen right here has 1 electron, this one has 1 electron, and this hydrogen has 1 electron. So both of the all 3 of the hydrogens have only 1 electron, and if you look on the periodic table, hydrogen is in group 1, so it only wants 1 electron. Therefore, all of those hydrogens are neutral. All right, so now let's do the aluminum. If you look at aluminum, aluminum is in group 3 on the periodic table, meaning it wants 3 electrons, and aluminum has 1, 2, 3. So if aluminum wants 3 electrons and has 3 electrons, it's actually neutral, right? There's no formal charge here. So a molecule of AlH3 is actually perfectly neutral, even though if you actually do the octet rule on aluminum, you would only count that it has 2, 4, 6 electrons, right? And because boron is in the same group as aluminum, boron would behave the same way. Boron only wants 3 electrons according to formal charge, and so a molecule of BH3 would be perfectly neutral because the boron has 1, 2, 3. Let me actually circle it because you can't see my fingers. So boron has 1, 2, 3 electrons. It's perfectly neutral. And every single hydrogen only has 1 electron as well, right? This hydrogen has 1 electron. This one has 1 electron. This one has 1 electron. So this molecule is neutral, even though it doesn't actually follow the octet rule, right? Remember, formal charge is going to tell you if a molecule is charged or not. And that's why aluminum and boron break the octet rule, because they don't need an octet rule to actually be neutral. Okay? So hopefully that makes sense. Right? Good. Alright, good. And was there one? Oh yeah, there was one other thing I wanted to say about formal charge. So what you might kind of gather, right? So remember, if you kind of look at it, right, like carbon and silicon. Oh shit! All right, so like group 4 is carbon and silicon. Group 5, nitrogen, phosphorus. Group 6, oxygen and sulfur. Group 7, the halogens. I'm not going to put all of them. I'll just put the first 2. And then group 8 is the noble gases. Okay. So anything in group 4, carbon, silicon, for example, wants a total of 4 electrons, right? So basically what that means is that carbon wants 4 bonds, okay? Because the only way for carbon to have 4 electrons according to formal charge, but 8 according to the octet rule, would be to have 4 bonds, all right? If carbon followed the octet rule, but didn't have 4 bonds, meaning carbon had, something that looks like this, that would be carbon following the octet rule. But if carbon only had 3 bonds, it would actually be formally negative. okay? So if carbon had only 3 bonds, it would be negative. Carbon can't have an expanded octet, so it can't really have more than 4 bonds. If carbon did not follow the octet rule, obviously it would just be a carbocation. Okay, and again, it would be a carbocation because from a formal charge perspective, this carbon down here only has 1, 2, 3 electrons, and it wants 4. So that thing is positive from a formal charge perspective and from an octet rule perspective, right? But I want to actually talk about sort of a shortcutty way that you can do some of this, right? So after carbon, so for nitrogen, so for group 5, group 6, group 7, carbon is really the only atom, carbon and hydrogen, that you're allowed to break the octet rule for. Again, I don't want to get into aluminum and boron right now, but sort of the main atoms that you guys are going to be working with, you're allowed to have a carbocation, and you're allowed to have like an H plus cation, but you are not really ever allowed to have nitrogen, for example, that's breaking the octet rule, or oxygen that's breaking the octet rule, okay? And so because of that, you can always assume that there's going to be enough lone pairs that the octet rule will be satisfied. And once you know that, you can actually just kind of really quickly assign the formal charges of things by just looking at how many bonds something has. So for instance, what I'm going to do, so I'm going to draw nitrogen with 2 hydrogens on it, and then I'm going to draw nitrogen with 3 hydrogens on it, and then I'm going to draw nitrogen with 4 hydrogens on it. Alright? So again, you will never see nitrogen breaking the octet rule. Okay? So all of these are going to follow the octet rule. That means for this first one, I need 2 lone pairs, because otherwise I would be breaking the octet rule if I didn't have 2 lone pairs. For the middle one, I need a single lone pair in order to not break the octet rule. And for the bottom one, I don't need anything. It's already satisfied by the octet rule. So let's do the formal charge. The formal charge for this one is 1, 2, 3, 4, 5, 6. Nitrogen wants 5. If it has 6, that means this one is formally negative. Right? This bottom one would be 1, 2, 3, 4, 5. It has 5. It wants 5. This bottom one is perfectly neutral. This next one is 1, 2, 3, 4. It has 4. It wants 5, so it's missing an electron. This bottom one is formally positive. Okay? Alright, so really quickly, let's go over and do oxygen. So oxygen, I'm going to draw oxygen with 1 hydrogen, 2 hydrogens, and then 3. Actually, you know what? I'm going to make this a little bit. Alright, give me 1 second. I found a way to organize this a little bit better. So, make that a little bit tinier. Alright, so I'm going to draw oxygen with only 1 hydrogen, with 2 hydrogens, or with 3 hydrogens. Okay. Alright, so basically just with 1 bond, 2 bonds, or 3 bonds. Again, in order to follow the octet rule, I would have to put 3 lone pairs on this one. Oxygen is never going to be breaking the octet rule, so assume that those lone pairs are there, if they're not explicitly drawn for you. I need to put 2 lone pairs here, and I need to put 1 lone pair there. Alright? So again, if I'm doing this guy right here, the formal charge on this oxygen would be 1, 2, 3, 4, 5, 6, 7. Oxygen wants 6, so if it has 7, that would mean that this one is formally negative. This guy right here, hopefully you realize water is neutral, but just to actually do it, it has 1, 2, 3, 4, 5, 6. Oxygen has 6, it wants 6, so water is perfectly neutral. That's why we can drink it and we don't get electrocuted. Alright, but let's look at this guy. This oxygen has 1, 2, 3, 4, 5 electrons. It wants 6, it only has 5, therefore this oxygen is formally positive. Okay? Alright, if I go over to the halogens, I'm going to draw a halogen with 0 bonds, and a halogen with 1 bond, and then a halogen with 2 bonds. Okay. Alright, and again, in order to follow the octet rule, I would have to give this one 4 different lone pairs. This one I would have to give 3 lone pairs. This one I would have to give 2 lone pairs. Alright. And again, if I assign the formal charge for all of these, this one would literally just be 1, 2, 3, 4, 5, 6, 7, 8. Chlorine wants 7, but it has 8, so that means this chlorine is formally negative. If I do this one, it's 1, 2, 3, 4, 5, 6, 7. Chlorine wants 7 and it has 7. Perfect, it's neutral. And then this one would be, let's see, 1, 2, 3, 4, 5, 6. So chlorine wants 7, it only has 6, therefore this one would be formally positive. Alright? So hopefully you guys recognize that there was a pattern here. Alright? Something like nitrogen, alright, if you ever see something in group 5, nitrogen and phosphorus want 3 bonds. So if you're looking at a molecule and it has nitrogen, if it has less than 3 bonds, it's going to be formally negative, and if it has more, it's going to be formally positive. Okay? And you can do the same thing with oxygen and the halogens, and you just have to shift everything up one, right? So nitrogen wants 3 bonds. And again, if you have 2 bonds, it's negative. 4 bonds, it would be positive. Oxygen wants 2 bonds. If you have less, meaning you only have 1 bond, you're going to be negative. If you have more, meaning 3 bonds, you're going to be positive. And the halogens, something like fluorine, chlorine, bromine, iodine, they only want 1 bond. And if you have less, meaning you have nothing, you're going to be formally negative. And if you have more, you're going to be formally positive, right? That's pretty much all I got about formal charge. Again, try to get really, really, really good at doing these quickly on your own. Alright, again, if you have to, you can use that, that little shortcut that I just gave you. But I want you guys to get really, really, really good at doing, all of these, right? So again, I'm looking at this one, oxygen. This oxygen, the middle oxygen right here, has 2 bonds, therefore it's neutral. The top oxygen has 2 bonds, therefore it's neutral. This nitrogen on the far right has 4 bonds, therefore I can rapidly assign that it's formally positive. And then I'm done, right? Alright, I really, really, really want you guys to get good at doing formal charge. Alright, so I did not actually think that I would spend that long talking about formal charge. I will do my best to try to speed this up a little bit. Okay, so after formal charge, next thing that I want to talk about with you guys is VSEPR, and then just in general, like local geometry, alright? So, not really a whole lot to talk about here. This is pretty easy, okay? So in order to do this, alright, what you need to do is you need to figure out the number of electron domains surrounding an atom, alright? And this is easier than it sounds, I promise. Surrounding an atom, okay? So a lone pair, that counts as 1 domain. And a bond, any bond, so it doesn't matter if it's a single, a double bond, or a triple bond. Double or a triple bond. They all count as 1 domain. Alright? So for example, if I have a molecule of water, alright, so this oxygen, the central oxygen, has 1 lone pair, 2 lone pairs, 3 bond, 4 bond. Alright? So lone pair, bond, bond. Therefore that oxygen, so the oxygen of water, has 4 domains. Alright? If I were to do the hydrogens, okay, so this hydrogen has 1 bond, that hydrogen also only has 1 bond, no lone pairs, so each of the hydrogens, so the hydrogens have one domain. Okay. Alright, so once you know how many domains something has, it's actually very easy to figure out what the geometry of that would be. And geometry is going to become really important in some of the mechanisms you guys are going to do. So if something has only one or two domains, it is going to be linear. Okay? Meaning the bond angle is a 180-degree bond angle. Alright? So for example, if I have this guy, which is a very powerful nucleophile, it's a cyanide molecule, that guy is linear, right? Because the carbon only has two domains, the nitrogen also only has two domains, okay? I could also have, I don't know, let me think of, pretty much anything that's triple bonded. I could have this guy. That guy's also going to be linear, okay? Because this carbon has two. Both of the central carbons have two bonding domains. Both of the hydrogens only have one. So voila. Alright? If you have three domains, then you are going to be trigonal planar. And this becomes very, very important. Okay? So trigonal planar means that you're going to look like a triangle. Alright, let's see, I'm trying to think of like a good so trigonal planar means that you're going to look, everything is going to be in the same plane. Everything, you're going to be perfectly flat, right? So that's the best way to think of trigonal planar. So if you take a molecule of acetone like this, okay, acetone, the central carbon and the oxygen are both going to be trigonal planar, right? Because this top oxygen is going to have one domain, two domains, three domains. Remember, the double bond only counts as one domain. You don't count both of the bonds as one. So this oxygen has three domains. And the central carbon also has three domains, right? The central carbon has one domain, two domains, three domains. And what that means is that the carbon is going to everything attached to the carbon is going to be in the same plane, and it's going to be in a triangle, right? Where the oxygen is one vertice, this other carbon is one vertice, this other carbon is one vertice, right? This is a nice triangle, and it's all flat. It's all in the plane of the board. And the oxygen is actually also going to be, right? Both of the lone pairs on oxygen are going to be in a triangle with the carbon, and they're all going to be flat, right? So three domains means that you are trigonal planar. And the last one, and I'm talking about this one last because it has a little bit of a caveat. So if you have four domains, all right, if you have four domains, you are almost always, okay, not always, but you're almost always tetrahedral. Alright? And honestly, you don't really need to know much about the shape of a tetrahedron. Tetrahedron is where you have one thing that's like coming out at you, and then another thing that's kind of going away from you. Alright? That's what a tetrahedron kind of looks like, okay? But the more important thing to know, alright, is that this rule does not apply. That's why I said almost always. Okay? So if, how do I want to word this? So if the atom has a lone pair, that can resonate, and I'm going to talk about resonance in a little bit, but if the atom has a lone pair that can resonate, i.e. it has a lone pair that is adjacent to a pi bond, right? So if it has a lone pair that's adjacent to a pi bond, then even if So even if it has 4 domains, it will actually be trigonal planar. And if you give me a little bit, I will explain to you why that is the case. But I just wanted to let you guys know that for now, alright? So that's really all I got to say about the geometry of things. But the next thing I talk about is going to be related to the geometry of things, okay? And that is, we're going to talk about hybridization, okay? So let me make a new page, alright? So we're going to talk about hybridization. So hybridization really goes hand in hand with geometry. It's super easy. If you are linear, then that means you are SP hybridized. Well, actually, you know what? I take that back. If you are SP hybrid, if you're SP hybridized, you're linear, but I haven't told you how to figure out hybridization. All right, let's talk about actually how to figure out hybridization. Sorry if my mind is kind of all over the place. I'm just kind of winging this. Also, it's 4:20. Hey, it's 4:20. Blaze. It's 4:20 a.m., so I'm kind of tired, but I do have a coffee. That was not meant for you to feel bad about me. All right, so I want to talk about hybridization, and specifically how hybridization is going to relate to molecular geometry. And hybridization is extremely important in organic chemistry, extremely important. So we need to figure out how to figure out what something's hybridization is. And it turns out that the way to figure out hybridization, you figure out hybridization exactly the same way you figure out geometry. Okay? Meaning, you count the number of electron domains. And once you know the number of electron domains, you know the hybridization of that particular atom, right? So in a molecule, obviously a molecule is going to have a bunch of different atoms. When we say what is the hybridization, there's no such thing as the hybridization of a molecule. We're talking about individual atoms of a molecule, okay? So if an atom in a molecule has one domain, okay, if an atom in a molecule has one domain, it's actually not hybridized at all. If it only has one domain, by definition, it would be just a plain old atomic orbital. Okay. But I don't know if you'll ever actually really encounter that. Let's actually talk about hybridized domains. If something has 2 domains, then that is going to be sp. That atom is going to be sp hybridized. Okay. If something has 3 domains, and remember from the last time, we know that if something has 2 domains, it's linear, which means that anything that is sp hybridized will be linear. Okay? If something has 3 domains, we say that it is sp2 hybridized. And we already know that something that has 3 domains is trigonal planar, so anything that is sp2 is going to be trigonal planar. And then now, I am about to tell you why we have that weird little caveat with 4 domains. So we already know that when something has 4 domains, it's usually tetrahedral, but sometimes it can be sp2. The same sort of caveat applies to hybridization. So if something has 4 domains, it is usually sp3, and when something is sp3, it is tetrahedral. But sometimes it will be sp2, and when it's sp2, it'll be trigonal planar. And that sometimes is what we already talked about before. So that applies when you have a lone pair that is adjacent to a pi bond. So let me give you some examples of that. Let's do some examples of all of them. So, for instance, something that, okay, so let's do like a hydride anion, right? So you can have a molecule called sodium hydride, which is Na plus and H minus, okay? So if you said, what is the hybridization of H minus, that would be a trick question. There's only one domain, so this H minus isn't a hybrid orbital. It's literally just the 1s atomic orbital, and both of the electrons are in the 1s atomic orbital, right? So let's do another one. Let's do something like, let's do my favorite cyanide anion, right? Okay. Alright, so in the cyanide anion, let's say we wanted to figure out the hybridization of the carbon and the hybridization of the nitrogen. So the carbon has one domain, two domains. So if the carbon has two domains, that means the carbon is sp hybridized. Alright, and let's do the nitrogen. The nitrogen has one domain, two domains. So the nitrogen here would also be sp hybridized. Okay? Alright, so we can do some more. I already kind of showed you this one, but let's do my favorite nail polish remover. Alright, so let's do the hybridization of the central carbon. Alright, so this carbon has one domain, two domains, three domains. Therefore, that carbon, so the central carbon right there, is going to be sp2. Alright, let's do a molecule of ammonia and figure out the hybridization of the central nitrogen. So in ammonia, the central nitrogen would have 1, 2, 3, 4 domains. If it has 4 domains, we know that this ammonia is going to be, okay, that looks like it's pointing at the lone pair. The nitrogen, also, you're right, lone pairs do not get hybridized. When we talk about hybridization, we're talking about atoms themselves. So this central nitrogen would be sp3. Okay, let me give you an example of what I mean when I say something that looks like it would be sp3, but because it can resonate, it's actually not sp3. So this molecule is a molecule that's called tetrahydrofuran. So if I asked you to tell me what the hybridization and the geometry of the central oxygen was, if you didn't know that little rule, you might say, okay, well, this oxygen has one domain, two domains, three domains, four domains. And then you would say, okay, well, because that oxygen has four domains, I'm going to say that it's tetrahedral and it's sp3 hybridized. But you would be wrong. And the reason you would be wrong is because if you notice, there's a double bond between this carbon and this carbon right there. Okay? And so because of the fact that the carbon adjacent to the oxygen has a pi bond, we say that this is actually sp2. Another way to say that is that the lone pair can resonate, right? So if I draw that lone pair, I can draw a resonance structure where that lone pair goes here, and then that double bond goes there, and then this double bond goes like onto that carbon, and I would get a resonance structure that looks like this. Okay. All right. And again, good practice. If you did not do the formal charges as fast as I did, try to get better at doing those formal charges, right? This oxygen has 3 bonds. We know that 3 bonded oxygens are positive. This carbon only has 3 bonds and a lone pair. We know that 3 bonds and a lone pair on carbon makes it formally negative, okay? If you are wondering why I said that that carbon has 3 bonds, remember there are these things called implied hydrogens. So this carbon had 1 implied hydrogen. I didn't do anything to that hydrogen. It's still there, right? So again, that carbon would have 1, 2, 3, 4, 5 electrons from a formal charge perspective, and it wants 4. That's why that carbon is negative. Okay. Anyway, hopefully you guys get the point. I'll do another example, right? So let's say you have like nitrogen right here, and I don't know, I have something like this. Okay. So again, you might be tempted to say, okay, this nitrogen right here has 1, 2, 3, 4 domains, and therefore it's going to be sp3. But even though it has 4 domains, it's not actually going to be sp3 because this lone pair can resonate. Right? And I can draw a resonance structure where that lone pair has resonated. Okay. And so because of that, this nitrogen, because it can resonate, this nitrogen is actually going to be sp2. And because it's sp2, it's actually going to be trigonal planar, not tetrahedral. Right? So again, I want to emphasize hybridization is really, really easy. Okay? The only little caveat is when you get down to this like 4, if it has 1, it's an atomic orbital. Alright? If it has 2 domains, it's going to be an sp. If it has 3 domains, it's going to be sp2. And if it has 4 domains, it's going to be sp3 unless you can resonate the lone pair. Meaning, unless the lone pair is adjacent to a pi bond. Right? The lone pair is on the nitrogen is connected to a carbon that has a pi bond. Right? The lone pair is on the oxygen is connected to a carbon that has a pi bond. Right? Those are going to be the only times where you have to worry about something has 4 domains, but for some reason it's actually sp2. And I say for some reason, but I actually want to talk about why that reason is, right? So why is it that, in this case, right, so let me redraw it, right? Why is it that if I have this molecule, right, why does this seemingly break the rule and go sp2? Well, the reason for that, right, is because if you guys remember when you were doing atomic configurations in general chemistry, electrons live in these little things called orbitals, right? And orbitals are actually really awesome. If you guys ever want to talk to me about what an orbital literally is, it's probably one of the coolest things in chemistry. It's probably not what you guys are expecting, but quantum mechanics is definitely not the subject for a video like this. But if you guys are curious about it, I would love to talk about it. I think quantum mechanics is like the coolest thing in the world. Anyway, for each energy level in an atom, right? So atoms have multiple little energy levels. So for each energy level, you have one s orbital, and you have 3 p orbitals. You also technically have 5 d orbitals, but in this Orgo class, we're not really going to be using d orbitals at all, so you really just need to know about this, right? So hopefully you guys remember that, right? When you were kind of doing your electron filling charts, right? It goes like 1s, and then 2s, and then 2p, right? And then like 3s, and then 3p, right? And then again, technically there's also 3d, but I don't want to draw that because we don't really use d orbitals in this class. But the point is, you always have 4 total orbitals, okay? At least if you're not, so long as you're not worrying about, a transition metal, you have 4 orbitals per energy level, 1s and 3p. And by the way, if you guys didn't know this, the reason that there's 3 p orbitals is because the p orbitals can be arranged in the axes of the 3 dimensions. So you have a py orbital, a px orbital, and then I suck at drawing 3-dimensional things, but you also have a pz orbital, which would be like the p orbital is three-dimensional. All right, so that's if you guys were ever wondering. I don't know. Maybe you weren't really curious. I'll get back on track. Okay, but the point is you always have 1s and 3p. So when you are sp hybridized, what that means, okay, so when you're sp hybridized, what that means is that you take one of the s's and one of the p's and you combine them into a new orbital that you refer to as sp, right? So I'm going to take these, and I'm going to make these two new orbitals called sp orbitals. But then hopefully what you guys realize is that you then have two p orbitals left over, right? And you guys are going to love this. Actually, I don't know that you guys are going to love this. I love this. But by the way, the fact that you have these two p orbitals left over is why when you have sp hybridization, you can typically get triple bonds, right? So again, one of my favorite examples is my favorite cyanide anion. So we've already done the hybridization. We know that both the carbon and the nitrogen are sp hybridized. So what that means is that both carbon and nitrogen have these two leftover p orbitals. And that's actually why they're triple bonded, right? So we know, so if you guys didn't know this, basically, sp orbitals and sp2, hybrid orbitals all essentially look kind of the same. There's not really a whole lot of difference between them. So they're all shaped kind of like, I don't really know what the shape is called, but they're kind of shaped like a sphere that you've just stretched out. So they look kind of like this. All right, that's basically what they look like. And like one of these lobes is shaded and the other one is not. So they all kind of look like this. So when you have a molecule like C triple bond N, right, you have the carbon, which has an sp3 orbital right there. And then technically there's a really tiny lobe right there. And then it has another sp3 orbital. So I'm going to draw my other sp3 orbital right there. And it has a really tiny lobe right there. Right? And the same thing happens with the nitrogen. Alright? Okay, so in order to make this a little bit less complicated, so I want you guys to know, technically, when you have an sp orbital, or an sp2, or an sp3, there's always going to be two lobes. So there's like a bigger lobe, and then there's like a tiny little knot-looking lobe. To make this simpler, I'm going to omit this bottom lobe, just because it's small, and it doesn't actually do anything in terms of bonding. It is there, but I'm going to just omit it to make these drawings look a little bit simpler. So like I said, carbon has an sp orbital here and an sp orbital here. Nitrogen has an sp orbital here and an sp orbital there. And holy shit, hopefully you guys can see, right? This lone pair is going to be in that sp orbital. The nitrogen lone pair is going to be in that s orbital. And these two sp orbitals is going to give me my first sigma bond. Alright? But if you remember, because it's only sp hybridized, both the carbon and the nitrogen have two p orbitals left over. So the carbon has a py left over, and the nitrogen also has a py left over. And when the two p orbitals interact with one another, you get a pi bond. And it turns out that both the carbon and the nitrogen also have the pz orbitals left over. And so therefore, you get a second pi bond. And that's why something like Cn, really anything that's sp hybridized, is capable of forming two pi bonds. Okay? All right, so now you guys know whenever you see a triple bond means that something is sp well, let me make this a new page. Okay? So when you have a triple bond, it means that you are sp hybridized. And the first bond is a sigma bond between the two sp orbitals. And the other two bonds are actually pi bonds from the leftover p's. Right? And you can actually apply that same logic to sp2 hybridized compounds. So let's take a molecule of ethylene. Oh shit. I want to draw this geometrically correct. So let's take a molecule of ethylene. Right? Okay. So we know that this carbon is, both of the carbons in fact, are sp2 hybridized. So when something is sp2 hybridized, what that means is that you take the s and two of the p orbitals and you merge them into these three hybrid orbitals that you call sp2. But again, what that means is that you have this leftover p orbital. Okay? So when you have a molecule of ethylene, you have the carbon, and again, I'm only going to draw one lobe, so again, when you have an sp2 orbital, okay, again, an sp2 orbital looks like this, alright, where you have a top lobe and a tiny bottom lobe. The bottom lobe exists, it's not involved in bonding, so I'm not going to draw it, just technically know that it's there. Okay. So when you have a molecule of ethylene, right, carbon has an sp2 orbital right there, and right there, and right there. This carbon also has an sp2 orbital right there, and right there, and right there, right? But again, the carbons, both of the carbons, have these leftover p orbitals, right? And the leftover p orbitals, holy shit, so the leftover p orbitals can form a pi bond, just like the sp2 orbitals can form a sigma bond. Okay? So that's why in a molecule of ethylene, there is a double bond between the two carbons. The first bond is the sigma bond between the two sp2 orbitals, and the second bond is the pi bond between the remaining p orbitals. Okay? And the other, the sigma bonds to hydrogen, they come from the bonds between the carbon sp2 orbitals and the hydrogen 1s orbitals. Okay. So that's how you get the bonding in there, alright? And then last, but certainly not least, if I have a molecule like ammonia, okay, right, in a molecule like ammonia, right, we know that that thing would be sp3. Obviously, if I am sp3 hybridized, it means that I took the s and all three of the p's and turned them into 4 sp3 orbitals. Now, because I took all of the p's, I don't have any p's left over. So when you're sp3 hybridized, you have no p orbitals left over. And what that means is if you have no p orbitals left over, it means you cannot form any pi bonds. So anything that's sp3 hybridized can only form sigma bonds, which basically means it can only form single bonds. Okay? But probably the more important thing to note, especially in terms of like a reactivity standpoint, is that it can't resonate. Because it turns out that hybrid orbitals, so sp, sp2, and sp3, these orbitals do not ever participate in resonance. Forgot how to spell for a little bit. They do not ever participate in resonance. Okay? the only orbitals that participate in resonance are p orbitals. So p orbitals participate in resonance. And now we're going to be able to get into why certain compounds that have 4 domains break that rule. Okay? Because resonance is extremely stabilizing. Okay? Very, very, very stabilizing. So let me give you an example. All right, so let's say I have this molecule right here. All right, simple molecule. All right. So I'm going to really quickly look at the hybridization of, sorry, let me put in the lone pairs on this oxygen. I'm going to really quickly look at the hybridization of this carbon right there, that carbon right there, and this oxygen right here, all right? So this carbon right here, okay, if you remember, there's implied hydrogens. So there's an implied hydrogen there and there. For this middle carbon, there's an implied hydrogen there, right? So the rightmost carbon is going to have 1, 2, 3 bonding domains, which means the rightmost carbon is going to be sp2, right? 3 bonding domains, never breaks any rules. So this carbon is sp2, okay? This middle carbon is going to have, let's see, oh shit. This middle carbon is going to have 1, 2, 3 bonding domains, meaning it also is going to be sp2 hybridized. Okay. Alright, now before I do the oxygen, I want to actually redraw this molecule, and I'm going to put in some orbitals, right? So we know that because both of the carbons are sp2 hybridized, it means that they have a leftover p orbital. Okay? Now, even though the oxygen has 4 bonding domains, if I hybridize the oxygen to sp3, what that would mean is that both of those lone pairs, right, this lone pair and this lone pair, both of those lone pairs would have to be in sp3 orbitals, right? Because if I have 4 domains and I have 4 sp3 orbitals, that must mean that every single domain is in an sp3 orbital. Both of the lone pairs are in sp3 orbitals, and both of the sigma bonds came from sp3 orbitals. And if it's in an sp3 orbital, meaning it's going to be sort of off-centered like that, sp3 orbitals cannot resonate with p orbitals, okay? But if I make it sp2, if I make this oxygen sp2 rather than sp3, then that allows me to have a leftover p orbital. And if I have a leftover p orbital, I can put one of the lone pairs in that leftover p orbital. So I'm going to make these p orbitals a little bit bigger. Right? I can put one of the oxygen lone pairs in that leftover p orbital. And once I can put it in a leftover p orbital, hopefully what you guys can see is that I now have a continuous chain of p orbitals, which, if you guys didn't know, whenever you have a continuous chain of p orbitals, that is what allows resonance to occur. Okay? So resonance occurs, okay? So resonance occurs because of the continuous alignment of p orbitals. If you don't have a continuous alignment of p orbitals, you can't resonate, right? So, for example, if I have, right, so the reason that something like this, right, you can draw a resonance, well, actually, you know what, let's do a classic one, let's do benzene. So benzene can resonate really well, right? So everybody knows that if you have a molecule of benzene, you can draw a resonance structure where the bonds just kind of shuffle around between the molecule, right? Okay. And the reason that that's allowed is because if you actually look at the hybridization of benzene, what you will see is that every single carbon, right, if I draw in my implied hydrogens, okay, you will see that every single carbon of benzene, all 6, are sp2 hybridized. And because they're sp2 hybridized, what it means is that every single carbon of a benzene ring has a leftover p orbital. And so rather than electrons being confined to 1 p orbital or 2 p orbitals, the electrons, which I'm going to represent by purple, the electrons can literally just kind of cycle their way around all of the p orbitals. It's like sort of a continuous track, all right? And the reality is that that is what is literally happening in benzene. In benzene, you don't have, you know, a 6-membered carbon ring. You don't have like 2 electrons confined to right there, and 2 electrons confined right there, and 2 electrons confined right there. What you actually have is all 6 electrons are kind of just like constantly circling around the ring, right? And they can circle around the ring because there's a continuous sort of highway of these empty p orbitals, okay? So I want you guys to understand that that is why, you know, certain things that can resonate, that's why they're going to break it. Because resonance is extremely stabilizing, okay? So resonance is extremely stabilizing. And so because of that, if something can rehybridize to make resonance possible, it will, right? So resonance is not possible with sp3 orbitals, which means anything that is sp3 hybridized can't resonate, because if you're sp3 hybridized, you only have sp3 orbitals, there are no p orbitals left over. So resonance is only possible with p orbitals, okay? All right. Now there's another interesting thing that I want to talk about related to hybridization, okay? And that is, and I think you actually go over this more so in Orgo I, but I want to just kind of refresh it. So if you know sort of what the hybridization of an atom is, then you should be able to tell me what orbital a lone pair lies in, okay? So this is also really important. You guys need to get really good at figuring out what orbital a lone pair is in, okay? So what orbital is a lone pair in? And we don't really ever need to talk about what orbital a bond is in, because by definition, a bond is its own orbital. We call them bonding orbitals. So a double bond, right, we've already kind of talked about this. A double bond is going to be 1 sigma and 1 pi. A triple bond is going to be 1 sigma and 2 pi's, and a single bond is just going to be a sigma bond. But when you have lone pairs can sometimes be in sp orbitals, they could be in sp2, they could be in sp3, or they could be in a p orbital. Or if it's a hydrogen, they could sometimes even be in an s orbital. But we want to be able to figure out rapidly what orbital a lone pair is actually in. What orbital is a lone pair in? Okay. And we can figure this out rationally if we think about what the question is that we're asking ourselves. Sorry, I had a hiccup. What the question is that we're asking ourselves, all right? So, this nitrogen, okay, if we look at it, we would see that it is, let's see, 1 domain, 2 domains, 3 domains. So what that means is that this nitrogen has 3 domains, so we know that the nitrogen is sp2 hybridized. We also know that if it's sp2 hybridized, that means it has 3 sp2 orbitals and 1 remaining p orbital left over. Which means that this lone pair right here could either be in one of the 3 sp2 orbitals, or it could be in the p orbital. And you might ask yourself, well, how do I know which one it is? Well, if you look carefully, you'll notice that nitrogen has a double bond. Nitrogen has a pi bond between it and this carbon right here. And the only way that you can form a pi bond, is with the overlap of two p orbitals. With overlap of, use my prepositions, with overlap of two p orbitals, okay? Right? So remember, right, a sigma bond is where electron density is held between the two atoms, okay? And so a sigma bond can really come from a lot of things. If you have, a sigma bond can be from like two s orbitals, so like s plus s will get you a sigma bond. Two px orbitals will give you a sigma bond. Okay. And then a bunch of hybrid orbitals will give you, right? So like, you can have, right, so like two SPs or two sp2 orbitals or two sp3 orbitals will also give you a sigma bond, right? Because the electron density, right, so if this is, atom A and atom B, carbon, right, atom A, atom B, atom A, atom B, right? So in all of these cases, the electron density, right, I'll put the electron density in blue, right? The electron density is between A and B, right? It's between A and B, okay, in all of these cases. So a sigma bond, there's a lot of ways to get a sigma bond. The definition of a pi bond, well, one of the definitions of a pi bond, okay, in a pi bond, the electron density is not sandwiched in between the two nuclei. The electron density is above and below the nuclei. So, right, in a sigma bond, if A was right there and B was right there, the electron density would be right here. But in a pi bond, the electron density is actually above it and below it. And the only way for that to happen is if you have two p orbitals. And when two p orbitals interact with one another, that's how you get a pi bond, okay? So, let me scroll down. I forgot actually where the hell I was going with this. Oh, yeah, sorry. So if we go way back up here, I had a little brain fart for why I was talking about that. So if we're trying to figure out where this lone pair is, right, the fact that this nitrogen already has a pi bond must mean that the nitrogen used its leftover p orbital to make that pi bond, right? And if it used its leftover p orbital to make the pi bond, then obviously that lone pair cannot be in the leftover p orbital. Okay? So if this lone pair was in the leftover p orbital, the nitrogen wouldn't have a p orbital to make this pi bond right here. So hopefully that makes sense to you guys. So basically what that means is that that lone pair must be in an sp2 orbital. All right? So that's sort of the logic, okay? But basically, if you know the logic, then you can kind of just do a little shortcut for yourself. So if something is sp2 hybridized, and has a lone pair, okay, if the atom already has a pi bond, so if the atom is already double or triple bonded, then what that means is that the lone pair must be in the sp2 in the case of the double, or in the case of triple, must be in the sp orbital, right? Again, okay. in a molecule of pyridine, the nitrogen is sp2 hybridized, but when you're sp2, you only have one p orbital left over, and that nitrogen already has a double bond. So this lone pair has to be in the sp2 orbital. All right. Similarly, if you have something like cyanide, okay, in cyanide, both the carbon and the nitrogen are sp hybridized, meaning they have two p orbitals left over. But even though they have two p orbitals left over, both atoms have two pi bonds. And so they had to have used those two p orbitals to make those pi bonds, meaning both of the lone pairs must be in one of the sp orbitals, not one of the leftover pi orbitals. Or sorry, one of the leftover p orbitals. Okay? An example, so going back up to this rule, if the atom is already double or triple bonded, then that means it's in the hybrid orbital. If you're sp2 hybridized and you have a lone pair, but the atom is not, okay, but the atom is not already double or triple bonded, then that lone pair would be in a p orbital. And again, that goes back to what we were talking about. The reason that it would be in a p orbital is so that it can resonate. So the atom is not already double or triple bonded. Then the lone pair would be in a p orbital. So an example of that would be, we go back to one of our friends over here. Okay. All right. Both of those. So this, well, actually, not both of them. Sorry. One of the lone pairs would be in a p orbital. Okay. All right. And remember, I'm putting this one in a p orbital so that it can resonate. Okay. So this oxygen right here would be sp2 hybridized. Meaning it would have 3 sp2 orbitals and 1 leftover p orbital. So this bond right here is going to come from an sp2 orbital, this one right here is going to come from an sp2 orbital, and then one of the oxygen lone pairs is going to be in an sp2 orbital, but the other one will be in that leftover p orbital so that it can resonate. Alright? And that's pretty much all I have to say about sort of figuring out where a lone pair is. Alright? Alright. Holy shit, I did not think this video would take this long. I apologize. I'm doing my best. I want to be thorough, and I want to teach you guys sort of everything that I think is important, so just bear with me. There's not a whole lot more stuff that I want to talk about, and I'll do my best to kind of sort of get on with the show. Alright, we just talked about hybrid orbitals. The next thing that I want to talk about is molecular orbitals. So hybrid orbitals, by the way, hybrid orbitals are just atomic orbitals, but they're just fancier. So hybrid orbitals are fancy atomic orbitals. So whenever you're describing a bond, bonds can come from hybrid orbitals in the same way that two atomic orbitals can combine to make a molecular orbital. Two hybrid orbitals can combine to make a molecular orbital. But hybrid orbitals themselves are just atomic orbitals, so fancy atomic orbitals. Okay. Molecular orbitals, on the other hand, these ones are going to be extremely important for when you guys are thinking about mechanisms. All right. So in this class, there's only really 4 molecular orbitals that you need to know. So there's a sigma orbital and a pi orbital, and there's a sigma star orbital and a pi star orbital. So the sigma and pi are bonding orbitals, and we physically draw them. We draw them, right? We represent them by the little lines, okay? Sigma star and pi star are anti-bonding orbitals, and we don't draw them, but they do exist, and it's really, really important for you guys to remember that they exist even though we don't explicitly draw them, okay? So I already kind of showed you a sigma orbital looks like this, okay, and a pi orbital Okay, if you want to get really technical, a pi orbital actually looks like this. But a lot of textbooks, and actually I agree, I think it makes it easier to view a pi orbital as literally just the p orbitals. Technically, it's the p orbitals sort of. Okay, so if you want to get a little bit more correct here, I guess, the p orbitals actually kind of like lean into each other a little bit, almost. Alright, and that's why you get something that looks like what I drew on the left there. Oh shit, Jesus, that's not good. Okay, yeah, now it's good. The shading is good, okay. Both of these are correct, okay. If you have one way, if one way sort of looks better to you, then do it that way. But both of these are equally valid as sort of representations of what a pi orbital looks like. Okay, but I want to talk about what a sigma star and pi star orbital look like, because you might not actually know that, because we don't ever draw them, okay? So if you have a molecule where A is in a sigma bond with B, right? Obviously the sigma orbital, if I were to draw the sigma orbital would be right here, all right? It would be right there. But the sigma star orbital, okay, so a sigma star orbital is actually it's actually like beyond, it's actually outside of the bonding axis. So this is what a sigma star, and hopefully that doesn't look super awkward, but that's what a sigma star orbital looks like, and I'll go ahead and shade these in, okay? So a sigma star orbital looks like that. Alright, so instead of it being between the two nuclei, it's on the outskirts of the two nuclei. And a pi star orbital sort of is going to do the same exact thing, right? So if I have A and B, right, a pi, right, so remember the pi orbital is when the shading was correct. And when the shading is correct, you get like a nice bonding interaction there and a nice bonding interaction there. When the shading isn't correct, okay, you will get a pi star orbital. And a pi star orbital is when the p orbitals are kind of like moving away from one another. Okay, so this is actually what a pi star orbital looks like right there. Okay? Okay, so why is that important? Okay, so, and again, right, so some rules, right? So anytime you have a sigma bond, you must have a sigma star bond. Okay, it's very, very important. And the same thing goes for anytime you have a pi bond, you must also have a pi star bond. We don't draw it, right? Obviously, if I draw, a molecule of water, I usually just draw it like this, right? You don't really ever see a molecule of water drawn like this, where there's a sigma star there, and a sigma star there, and a sigma star there, and a sigma star there. But you have to realize that these sigma star orbitals, which are antibonding orbitals, they're empty. There's nothing in them, but they are still there. Okay? They exist. Alright, so all four of these sigma star orbitals still exist. Alright? Okay, so they're still there. Alright? Alright, so let's talk about thinking about some of these orbitals, right? So let's take a molecule like H2, right? So when you have a molecule of H2, you have a 1s orbital, just like that, okay? So there's a hydrogen right here, and a hydrogen right there. And when those two hydrogens come together, those two 1s orbitals, they combine with one another. And if we look at a molecule of H2, we would be able to tell that there is one bond. And because there's one bond in H2, we know that it is a sigma bond. So therefore, we know that we must have combined them to get a sigma bond And also, anytime we make a sigma bond, we have to make a sigma star bond. Alright? So, in something like H2, this is pretty easy, okay? So, if we were to draw the molecular orbitals of H2, right? So the sigma orbital is going to look like this, where you have hydrogen, a nice sigma bond, and then hydrogen. And the sigma star orbital of H2 is going to look like this, where you have hydrogen, and then all of the electron density is actually on the outskirts. Okay? Right? So something like H2 is a little bit easier. But now I want to do a different example. And I'm going to do a different example because I want to actually illustrate a point. All right? So I actually want to do, I want to look at the molecular orbital diagram. Instead of H2, I want to actually look at the molecular orbital diagram for something like OH minus. Right? So OH minus is also diatomic. I did that so that it was kind of easier. So we can do oxygen over here and hydrogen over here. Okay. Now the hydrogen only has, right? So okay. I guess if I look at the bond here, right? It's a single bond, which means it's going to ultimately. I know that I ultimately am going to get a sigma and a sigma star. All right. So the hydrogen is. The hydrogen only has one bonding domain, so I know that the hydrogen, because it only has one bonding domain, it's actually not hybridized at all. If you remember way back, like I said, at this point I've made so many pages, I don't want to scroll all the way up, but remember, if you only have one bonding domain, you're actually just atomic hybridized, or I guess not hybridized at all. So the hydrogen is just going to have its 1s orbital. Let me erase that. The hydrogen is going to have its 1s orbital. Okay. And the oxygen has 1, 2, 3, 4 bonding domains. Therefore, it's going to be sp3 hybridized. So the oxygen is going to have 4 sp3 orbitals. And for now, I'm going to draw them sort of perfectly on the level of the hydrogen 1s orbital, but I'm going to change that once I sort of get on with this. All right. So anyway, we know that 3 of the 4 orbitals that oxygen has, right, are just going to be occupied by lone pairs, meaning that they are not involved in bonding at all. So these 3, I'm just going to put like an X through them. They're not going to wind up being involved in any bonding. They're just going to stay as sp3 orbitals. But ultimately, one of the sp3 orbitals from oxygen is going to combine with the 1s orbital of hydrogen to form a sigma bond and a sigma star bond. Okay. Right. And again, we know that hydrogen has 1 electron. Oxygen is going to have 1 electron in one of those sp3 orbitals. Okay. Actually, sorry, it's O minus, so it actually is going to have 2 electrons in that orbital. Right. Oh, actually, no. Oxygen wants 6 electrons. Okay, so I shouldn't have put the X's there because it's messing me up. Alright, so oxygen is in group 6. Okay. So oxygen normally has 2 electrons in the s orbital, and then 1, 2, 3. So oxygen normally has that electron configuration. When it's O minus, it means that there's an extra electron, which means that there's actually that many. Alright. 1, 2, 3, 4, 5, 6. Sorry, I really can't do math. Oxygen normally has this electron configuration, but when it's O minus, it's going to have an extra electron there. There we go. Alright, sorry I butchered that. Okay. So these 3 are not going to be involved in bonding, which is why they're going to stay lone pairs in an sp3 orbital. Okay. But this one right here can combine with that one. Okay, so the sp3 of oxygen can combine with the 1s of hydrogen. Now, one thing that I want to reiterate, well, not reiterate, because I guess I haven't said it yet. Oxygen is way more electronegative. Okay. And by the way, anytime I use electronegativity or electronegative, I'm going to use this symbol right here. So this is the symbol for electronegativity. And it's a lot easier for me to write out that symbol than it is for me to constantly write out the word electronegativity. So oxygen is way more electronegative than hydrogen. And what that means, from an energetic perspective, is that oxygen once, so the sort of the definition of electronegativity, or not the definition, but one way to think about electronegativity is the fact that oxygen is more electronegative than hydrogen. What that means is that oxygen wants electrons more, so I'll say oxygen being more electronegative implies that oxygen wants electrons more than hydrogen. And what that implies is that electrons are more stable. Electrons are more stable in oxygen's orbitals than they are in hydrogen's orbitals. And so before, when I was trying to figure out a molecular orbital diagram for OH minus, right, I kind of drew the 4 sp3 orbitals of oxygen. I drew them sort of on the same energy level as hydrogen. But oxygen is more electronegative. And if oxygen is more electronegative, it means that the electrons want to be in oxygen more so than they want to be in hydrogen. What that means is that they're more stable, they're lower in energy. So what that means is that the hydrogen 1s orbital is actually somewhere like up here, okay? So now the energies are not symmetric, and a really cool thing happens when the energies are not symmetric. So they still combine, right? So I still get a sigma and a sigma star orbital, okay? Okay, so I still get a sigma and a sigma star. But now, what I'm going to do is I'm actually going to redraw what the sigma and the sigma star look like. So hopefully what you can see here is that the sigma orbital is closer to the oxygen orbital, right? So it's closer to the oxygen than it is to the hydrogen, okay? And what we say, the language that we use in organic chemistry, is that we say the oxygen contributed more to the sigma orbital than the H. And likewise, you'll notice that the sigma star orbital, right up here, is much closer to the hydrogen than it is to the oxygen. So what we say is that the hydrogen contributed more to the sigma star than the O did. And what that means is that before, so we already know that, if I have a molecule of H2, the sigma orbital looks like that, where it's perfectly symmetric, okay? And the sigma star looks like this, where it's also kind of perfectly symmetric. But when it's not symmetric, it actually changes the shape of the orbitals, and specifically it changes the shape of the lobes of the orbitals. So because the oxygen contributed more to the sigma orbital than the hydrogen, what that means is that the electron density is shifted more towards the oxygen than it is towards the hydrogen. So the sigma orbital of something like an OH is actually going to look more like that. Where if you imagine, you kind of like take the electrons of the hydrogen and like shove them over to the oxygen, okay? So it's going to look like that. And the sigma star orbital, because we said that in the sigma star, so in the sigma star, the H contributed more. What that means is that the lobe of the sigma star will be small on the oxygen, but very, very large on the hydrogen. And this becomes extremely, extremely important. Actually, I'm going to give you an example of when this becomes extremely important. So we're going to go over eventually in this video what makes something a good electrophile, but hopefully you guys know that halogens are very good leaving groups. And what that means is that the carbons connected to a halogen are really good electrophiles, all right? Now, if the last, 10 minutes of me, however long I've been going on about molecular orbitals, I feel like I've been talking about it for a little bit, if that confused the shit out of you, please don't let it. You're certainly not going to be expected to draw molecular orbital diagrams for every single organic molecule you see. And in fact, I don't want you to. I don't think that that's necessarily help you. The only reason that I went into this is because I want you to be able to look at a molecule and very quickly determine what its where the bonding orbitals are and where the non-bonding orbitals are and what they look like. So for example, if I gave you this molecule, all right, what I would hope that you guys would be able to do is you would be able to say, okay, if I'm looking at this bond right here, okay, that is a carbon-chlorine sigma bond, and therefore there must also be a carbon-chlorine sigma star bond. And what I want you guys to do is I want you guys to know sort of where those orbitals are in space. So obviously the sigma orbital, we literally drew it. The sigma orbital is the bond itself, right? So we don't really need to think about how to draw the sigma orbital because by definition it's sort of already there. But I want you to think about where the sigma star orbital is. Remember, the sigma star orbital is outside of the two, right? So the sigma star orbital is right there. But again, hopefully you guys know that the electronegativity of chlorine is much greater, much, much, much greater than the electronegativity of carbon. And because of that, you actually wouldn't draw the orbitals as the same, right? Right? You wouldn't draw the lobes of the orbitals, right? So remember, if chlorine is more electronegative than carbon, so if I have carbon right here and chlorine right over here, right? So chlorine is more electronegative. That means that chlorine's orbitals are going to be maybe down here. Carbon's orbitals are going to be maybe up here. So when I form a bonding and an antibonding orbital, and it doesn't even matter where the electrons are, right? When I form a bonding and an antibonding orbital, the bonding orbital is going to be much larger on the chlorine side, but the antibonding orbital is going to be much, much, much larger on the carbon side. So what this means is that when you have a molecule like, ethyl chloride, there's a tiny little hole, right? A tiny little antibonding orbital right there, but there is a huge, huge antibonding sigma star orbital on the carbon side. And you guys all know this because you guys all remember probably the first reaction that you ever learned in Orgo 1 was an SN2 reaction, where if you have something like this and you have a really good nucleophile like OH-, you guys learned that it does a backside attack, which then expels out the leaving group. And now you guys know why it does the backside attack. It does the backside attack because that's where the empty orbital is. Electrons need to live in orbitals. And there's a massive orbital right on the backside of that carbon-chlorine bond. So obviously those electrons are going to want to populate that nice empty orbital. Which brings me into my third and final point about, sort of these molecular orbital rules. If you fill an antibonding orbital with electrons, if you fill an antibonding orbital with electrons, okay, the corresponding bonding orbital must break. So the corresponding bonding orbital has to break. Must break. Okay? Right? So in this mechanism, right, you could ask yourself, well, why does the chlorine have to leave, Brian? Well, the reason it has to leave is because if I start dumping into the carbon chlorine sigma star, the carbon chlorine sigma has to go bye-bye. Okay? That is like a fundamental principle of quantum mechanics. You cannot have both a bonding orbital and an antibonding orbital that both have electrons in them. That doesn't work. Okay? So the moment you start filling an antibonding orbital, you must actually break the corresponding bonding orbital. Alright? So it's very important that you guys know that. Alright? Alright. So we're doing good. Okay. The next thing that I want to talk about, it's technically related to molecular orbitals. I'm really sorry, but it's probably the last thing that I'm going to talk about from a molecular orbital standpoint. The two, so in organic chemistry, we only really care about two molecular orbitals. So the two most important molecular orbitals that we care about, we have special names for them. So they are the HOMO and the LUMO. Okay? The HOMO is the highest energy orbital. The highest energy molecular. Well, it's not always a molecular orbital. The highest energy orbital that actually has electrons in it. Okay? And the LUMO is the lowest energy. Usually, it sometimes can be an atomic orbital. It's usually an antibonding orbital, but it technically could be an atomic orbital. But the LUMO is the lowest energy orbital that has no electrons in it. Okay? Right? So just like you can have electron configurations for atoms, you can have electron configurations for molecules, right? So I'm not gonna. Let's just draw a molecule of acetone. Okay. Now the reality is that acetone is going to have an absolute shit ton of molecular orbitals, and I don't really feel like worrying about them. But all I'm going to care about is the highest occupied orbital and the lowest unoccupied orbital. All right. So first of all, if I'm looking at a molecule of acetone, what I kind of want to tell myself, okay, is that it looks like there's 1, 2, 3 sigma bonds. And then it looks like there's 1 pi bond. And then it looks like there's 2 lone pairs. And sort of by definition, a lone pair is going to be in an atomic orbital, either an unhybridized or a hybridized atomic orbital. And we already talked about how to figure out if it's in a p orbital or one of those hybridized orbitals. Okay? So, hopefully, it makes sense to you guys that a bond is a stable arrangement. Okay? So, bonds will always be lower energy than lone pairs. Okay? So bonds are more stable than lone pairs. If bonds were not stable, then molecules wouldn't exist, right? All elements would just be flying around as individual atoms. I wouldn't be making this video, you wouldn't be around to hear me make this video, this computer wouldn't exist, nothing would exist, okay? Just atoms, just elements would exist. So bonds are more stable than lone pairs, and a sigma bond is more stable than a pi bond. Almost always. Again, there's some weird exceptions, but almost always a sigma bond is more stable than pi bonds. Okay, so there's another thing, and that is that, if I have like an energy diagram, right? So I'm going to put my sort of non-bonding orbitals right here. So non-bonding, otherwise known as just atomic or hybridized orbitals. Okay. So they're going to be, I would call that like the 0 point of energy. Okay. And then pi bonds are more stable than that. But sigma bonds are even more stable than that, right? So in terms of energy, sigma bonds are the most stable, and then pi bonds, and then sort of no stability at all, or would be just, lone pair, okay? And then it turns out that antibonding orbitals are symmetric with respect to energy to the corresponding bonding orbital. So what that means is that even though a sigma is more stable than a pi star, oh shit, wrong color. A pi star is not as unstable as a sigma star, right? So all I want you to get out of this is I want you guys to understand or sort of have a grasp on this relative order, okay? So from most stable to least stable, it goes sigma, which is more stable than pi, which is more stable than SP or SP2 or SP3 or P, which is more stable than pi star, which is more stable than sigma star. All right. So I want you guys to just be good at recognizing that order. And then once you know that order, it's actually really easy for you to kind of look at a molecule and figure out what its HOMO and LUMO would be. So if you look at a molecule like acetone, hopefully you would realize right away that the HOMO is going to be the lone pairs on the oxygen. Okay? And specifically, remember, HOMO refers to an orbital, so it would be whatever orbital those lone pairs were in. And again, we already talked about how to figure out what orbital a lone pair was in. Okay? So the HOMO is going to be the lone pairs. Okay? Now, the LUMO, okay, so if we wanted to figure out what the LUMO was, the LUMO is usually going to be an antibonding orbital, and because we have a pi star, remember, pi star is much more stable than sigma star, so the LUMO here is just going to be the pi star orbital between the carbon and the oxygen. Alright? Perfect. Okay. Alright. So another example, right, if I have my molecule of ethyl bromide, okay, so we have a bunch of molecular orbitals here, alright, so we have, I'm just going to say, we have a bunch, that's not how to spell bunch, we have a bunch of carbon, hydrogen, sigma orbitals, we have a bunch of carbon, hydrogen, sigma star orbitals, and then we have one carbon, bromine, sigma orbital, and then we have one carbon, bromine, sigma star orbital, and then obviously the bromine is going to have a bunch of lone pairs, which means we also have a bunch of non-bonding orbitals, which those lone pairs are going to wind up being in. Okay. So again, if I was trying to figure out what the HOMO of this molecule would be, it's definitely going to be these non-bonding orbitals, right? Because, right, like, a non-bonding orbital is going to be higher energy than the sigma orbitals. And even though the non-bonding orbitals are lower energy than the sigma stars, by definition of them being sigma stars, don't actually have electrons in them. So the highest energy orbital that has something in it is going to be whatever orbitals these lone pairs are in. And if you forgot, we can really quickly do that. The bromine has 4 bonding domains. If it has 4 bonding domains and it isn't adjacent to any kind of pi bond, that means it's going to be sp3 hybridized. That means that every single lone pair is going to be in an sp3 orbital. So the HOMO of that molecule would be the sp3 carbon bromine. Or sorry, I said that wrong. sp3 is not a molecular orbital. Jesus. It would just be the sp3 bromine orbital. So the HOMO is the sp3 orbital on bromine. Okay. Now for the LUMO, right? Obviously the LUMO, you would say, well, it's going to be one of the sigma stars, right? It's either going to be the C to H sigma star or the C to Br sigma star. And to figure that one out, okay, again, you just have to remember sort of what we talked about with electronegativity. So the electronegativity of bromine is going to be greater than carbon, which is going to be greater than hydrogen, right? So the carbon-bromine sigma star orbital, so right, bromine would be like down here, carbon would maybe be up here, versus the carbon-hydrogen sigma, so this would be like carbon, well, I'll do it in order. This would be like bromine, carbon, and this would be carbon, hydrogen. So carbon would be like up here, hydrogen would be up here. Okay, so when carbon and bromine form a sigma and a sigma star, all right, because the overall energy is lower, both the sigma and the sigma star is going to be pretty low. All right. But because the carbon and hydrogen are much higher in energy, the resulting sigma and sigma star will be higher. So it should make sense to you that the LUMO is going to be the carbon-bromine sigma star, because that sigma star is going to be lower in energy than the carbon-hydrogen sigma star. Okay. Which means in a molecule like this, the LUMO is going to be, and again, right, the sigma star is much more contributed by the carbon than it is by the bromine, which means the sigma star is going to be huge on the carbon, not very big on the bromine. Okay? So that is going to be the LUMO. And the lone pairs on the bromine, which are in an sp3 orbital, that's going to be what the HOMO is. Okay? And now, I think I said this a lot, but now I actually, well, at least for now, I think I fully mean it. This is the final thing that I'm going to say about molecular orbitals. Whenever we talk about HOMO, that's when we are talking about the nucleophile. So the nucleophile, whenever you're doing a reaction and I ask you, what is the nucleophile? You should be thinking about what is the HOMO. And the LUMO is always going, and the LUMO is always going to be the electrophile. Okay? So that is why when we have a molecule, when we have, an SN2 reaction, like hydroxide reacting with this, right, and we can draw a mechanism for it, we can say that goes there, and that goes there, to produce this molecule. Okay. Right? Right, we can say, in a more sort of exact way, rather than just using arrow notation, right? We can describe this from a molecular orbital standpoint, which would mean, which would mean that we can say that the sp3 orbital, so the sp3 orbital of OH minus dumped into the sigma star carbon bromine orbital, which broke the sigma carbon bromine orbital, right? And resulted in a new sigma orbital, a new sigma C to O orbital. Okay. So it's just a way to view a reaction and to view a mechanism of a reaction, not just via arrow pushing formalism, but also via the reality, which is that, you know, reactions happen because molecular orbitals are mixing with one another. You know, arrows are just a formalism. You know, there are not like millions of arrows flying around in your body right now, right? And I think you guys knew that, but I want you to, you know, really be aware of that. Okay. All right. Moving on. The next thing I want to talk about. Okay. So the next thing I want to talk about, and this one is going to be really fast, I promise. Okay. Oh gee, that's really fucking big. Christ. All right. So the next thing I want to talk about is, why the fuck did I zoom in that much? Jesus. All right. Oh, sorry. I know why it was doing that. My bad. It's new technology. Don't yell at me. All right. So the next thing I want to talk about really quickly is carbocation and carbanion stability. Okay, you guys are going to need to know these really well. All right. So this is super fast, super easy. Okay. So with carbocation stability, the order, so from most stable to least stable, so it goes resonant stabilized, is more stable than tertiary, which is more stable than secondary, which is more stable than tertiary, which is more stable than methyl. So what I mean by that is that if you have that thing is going to be slightly more stable than that thing, which is going to be slightly more stable than that thing, which is going to be slightly more stable than this thing, which is going to be slightly more stable than literally like CH3+. Okay. If you want to, I could explain the reasoning. This video is already super long, so I don't want to get super into the reasoning behind it. But if you want to look it up, the reasoning has something to do with a phenomenon called hyperconjugation. But again, if I actually went into it, I would probably spend 15 minutes explaining it, and I don't want to do that with you. So I should say hyperconjugation is the reason why, like, tertiary is more stable than secondary, which is more stable than primary, which is more stable than methyl. The reason why resonant is the most stable is because resonance is not hyperconjugation. Resonance is like actual conjugation. All right. So when you are resonance stabilized, instead of that positive charge being confined to just one atom, it can be spread out, right? So I can draw a resonance structure where that double bond goes over there. And what that allows me to do is delocalize that positive charge. Instead of the positive charge being confined on this atom right there, it's now being spread out over a 1, 2, 3 atom framework. And actually, I could draw another resonance structure where it winds up, where the positive charge winds up on this carbon, and then I could draw a fourth resonance structure where it winds up on this carbon. If you don't believe me, you could try to draw them out yourselves. But the point is, okay, so resonance is the most stable carbocation, followed by tertiary, followed by secondary, followed by primary, followed by methyl, right? And you guys could probably guess this if you didn't already know it, but carbanion stability is going to almost be exactly the opposite. So it turns out that resonance is really fucking good, and resonance will stabilize any charge, not just positive charges. So for carbanions as well, resonant stabilized carbanions, are going to be more stable than methyl, which is going to be slightly more stable than primary, which is going to be more stable than tertiary, which is going to be more stable, than secondary, which is going to be more stable than tertiary, right? Okay, so again, if I have a resonance, so instead of a benzyl resonance, I'll just draw like an owl-based thing. Okay, so this thing is going to be more stable than that thing, which is going to be slightly more stable than oh shit, that's a secondary, which is going to be slightly more stable than that thing, which is going to be slightly more stable than this thing, which is going to be slightly more stable than this thing right here. Okay? Alright? And again, the reason why these are getting increasingly more unstable is because of hyperconjugation, which is not good. It's good in the sense of cations. It's bad in the sense of anions. But this one is not hyperconjugation, it's actual conjugation, which means that negative charge can be delocalized. So, right, if I have a lone pair that's negative, I can actually move that lone pair there and then move this double bond on that carbon. And that would generate this resonance structure. So again, rather than having a full-fledged positive charge on one carbon atom, I've spread that extra electron density out over a 1, 2, 3 atom framework, which is going to make that much more stable. All right. And I believe that's pretty much all I have to say about what's it called? Carbocation and carbanion stability. All right. So the next thing that I want to talk about. Alright, so this is going to be like sort of the tail end of this video, so congrats if you've made it this far. I want to talk about, because it's probably one of the most, if not the most important aspect when you're trying to write mechanisms, is I want to talk about how to determine what your nucleophile and electrophile and leaving group are, okay? So the first thing I'm going to talk about is how to determine what your nucleophile is, okay? So, by the way, a nucleophile, that's going to be something that is electron rich, okay? And there's essentially, I would say, 3 types of nucleophiles. So the first type of nucleophile is going to be a lone pair, all right? Now, nucleophiles can come in a range of strengths, right? You can have, strong nucleophiles, weak nucleophiles. So let's talk about this. So a lone pair is going to be a nucleophile, okay? However, a bigger atom, so a lone pair on a bigger atom is going to be stronger than a lone pair on a smaller atom, okay? Right. Also, a lone pair on a not very electronegative atom is going to be more nucleophilic than a lone pair on a highly electronegative atom. And I'll talk about these rules in a minute. I just kind of want to get these out of my head and onto the screen. And the third thing is that a negative lone pair will be more nucleophilic than a neutral lone pair. Okay. Alright, so let me give you some examples of these. So what I mean by this is that, something like OH minus is going to be more nucleophilic than something like water, even though in both cases I have a lone pair on an oxygen. For number 2, something like, ammonia is going to be more nucleophilic than water. Both of those are neutral, but nitrogen is less electronegative than oxygen. And then for this last one, let's see, something like iodide is going to be much more nucleophilic than something like fluoride. And technically you could also argue that this is also because iodine is much less electronegative than fluoride, but in this case it actually does have more so to do with the size than the electronegativity per se. So really quickly, I just want to talk about why these rules exist, okay? So if you're really, really large, right, so nucleophilicity, literally, it refers to how easy it is for the electrons in that orbital to delocalize themselves into an antibonding orbital or into whatever the LUMO is. And so hopefully it makes sense to you that if you are in a very, very large orbital, it's easier for you to find an antibonding orbital than it is if you were in a small orbital, okay? It's kind of like if you were trying to like shoot a bullseye and you had like a super large bullet versus if you had like a super microscopic bullet, okay? So the bigger the atom is, the orbitals themselves are usually going to be bigger, and therefore the easier it is for that HOMO to find the LUMO. So that's really the explanation for rule number 1. For rule number 2, the other thing, there's another reason why bigger atoms are more nucleophilic, and it has to do with this concept called polarizability. But I don't really think in this class you really need to know that much about polarizability. So I would just think of it as, if you're in a bigger atom, you have a bigger orbital, and bigger orbitals are more able to find antibonding orbitals. For the next one, the reason why less electronegative atoms are more nucleophilic than more electronegative. So if you remember, the definition of electronegativity is how badly you want to sort of keep the electrons that you have. And a nucleophile, again, sort of by definition, a nucleophile is something that is electron rich. A nucleophile is trying to donate its electrons to some kind of antibonding orbital on a different atom. And so what that means is that if something is really electronegative, like oxygen, for example, is really electronegative, oxygen does not want to give its electrons away. Okay, if I have like, H2O, right? That lone pair on that oxygen, it wants to stay on that oxygen. It doesn't necessarily want to get dumped into some random antibonding orbital somewhere. Whereas something like NH3, nitrogen isn't as electronegative as oxygen. So nitrogen has no problem, right? If I have this nice big antibonding orbital right there, nitrogen has no problem saying like, yeah, I'll share my electrons with that antibonding orbital, right? And then the final reason, if you have obviously something that's negatively charged, hopefully it makes sense to you that if something is negatively charged, it's going to be more positive loving than like a neutral thing. And I don't really know how else to explain that. Just, negatively charged things love positively charged things. It's just kind of the way the world works. All right. Okay, so that's step 1. Is that the one type of nucleophile is going to be a lone pair. All right. The other type of nucleophile is going to be a carbon-carbon pi bond. Okay. And this is really important that you notice that it's a carbon-carbon pi bond. Carbon-oxygen pi bonds are not nucleophilic. It's just a carbon-carbon pi bond. And there's really actually nothing else to really talk about with this one. There's no sort of special, I don't have like a sub 1, 2, and 3 like I did for the lone pair one. Just recognize that whenever you're dealing with alkenes or alkynes, that technically this pi bond and these two pi bonds are nucleophilic. Now, one thing I will say is that a carbon-carbon pi bond, these are weak nucleophiles. Okay. So pretty much all of these are weak, but they are still there, and they will react with electrophiles if the electrophile is powerful enough. Okay, the third and final example of a nucleophile is going to be a carbon-metal sigma bond. Okay. Well, it doesn't actually. It can be either a carbon-metal. Sometimes they're actually hydrogen-metal sigma bonds as well. But that's actually going to be the third example. So you see these all the time when you're working with things like Grignard reagents. Okay, so Grignard reagents, lithium aluminum hydride is an example of this. Sodium borohydride is an example of this. Okay, so in all of these cases, you have either carbon or hydrogen that is connected to a metal. So in a Grignard reagent, the metal is magnesium. So this sigma bond that I just highlighted would be nucleophilic. In lithium aluminum hydride, you have aluminum that's bonded to hydrogen. That bond is nucleophilic. And same with sodium borohydride. The bond itself is nucleophilic, so the sigma bond is nucleophilic. One thing I always recommend people do, if you're confused about sort of the mechanisms for how these types of nucleophiles would operate, whenever you see a Grignard reagent, the easiest way to think about sort of what it is and how it's going to react is basically take the bond to MgBr. Okay, so imagine you just sort of put a box around the bond MgBr, and basically just pretend that that box, basically just pretend that that part of the molecule didn't exist, and then put a lone pair and negative charge on the remaining part of the molecule. Alright, so what I mean by that is, like, if I had this molecule right here, MgBr. Alright, now you guys know that this sigma bond is the actual nucleophile, but sometimes it can be a little bit confusing thinking of a bond as a nucleophile. So if that's confusing to you, what I want you to do is I want you to take that molecule and I want you to just pretend that that bond to MgBr doesn't exist. And then instead, so draw what you have, which is just this. And then where the box is, just put a lone pair and a negative charge. Okay? So again, so what I mean by that is that this, right? So this molecule and this molecule, the molecule on the left and the molecule on the right, they're essentially going to behave the exact same way, right? All right. Same with whenever you see lithium aluminum hydride, just think of it as H minus. It's not technically H minus, but it can be helpful to think of it like H minus. Same with NaBH4, just think of it as H minus. Okay. Now, one thing that I do want to say is that just like I had to do like a 1, 2, 3 for lone pair, I do need to do a 1, 2, 3 for the sigma bonds. So sigma bonds to metals can be nucleophilic. Okay. Okay. So this one is important. So all right. Sorry. The less electronegative the metal is, the stronger the nucleophile. All right. The stronger the nucleophile, and that is why. Okay, if you actually look up the electronegativity, so boron is more, so the electronegativity of boron is greater than the electronegativity of aluminum. And that is why lithium aluminum hydride is a stronger nucleophile than sodium borohydride. Okay. It's also why, so you guys have worked with, or you guys have seen reactions where you've used a Grignard before. So Grignards are one example of like this carbon-based nucleophile. Grignards are not as strong as another thing that you can have, which this class of molecules is called alkyl lithiums. So alkyl lithiums are they do the same thing as Grignards, right? So again, if I were to see this molecule, this Grignard right here, I would just in my head tell myself that it was this molecule right here. And I would do the same thing for this alkyl lithium. Now again, neither the Grignard nor the alkyl lithium is actually, an ethane carbanion. However, this guy, so the alkyl lithium, is much, much, much closer to being this than the Grignard is. And so the alkyl lithium is a stronger nucleophile, right? And that is because the electronegativity of magnesium is greater than the electronegativity of lithium. Okay. So I think that's all that I have to say about nucleophiles. So again, just to recap, in order for something to be nucleophilic, it's got to have either a lone pair, a carbon-carbon pi bond, or a carbon or hydrogen metal sigma bond. All right. And again, we talked about, based on lone pairs, there's ways to order whether or not they're strong or weak. Same with when it's a carbon metal or hydrogen metal sigma bond, there's ways to order whether it's strong or weak. Okay, that takes care of nucleophiles. Really quickly, I want to talk about before I talk about electrophiles, I want to talk about leaving groups. So, how to identify whether or not something will be a leaving group? Leaving groups are pretty easy, okay? So leaving groups are things that would be stable. Things that would be stable if they lost a sigma bond and gained a lone pair. Okay. So that is the definition of a leaving group. Okay, so how do you figure out whether or not something would be a good leaving group? So good leaving groups, there's essentially only really like 3 types. Okay, so good leaving groups are the conjugate bases. So the conjugate bases of the strong acids. Okay, so if you guys do not remember the strong acids from Gen Chem, that's totally fine. I'm going to write them down for you. So the strong acids are HCl, HBr, HI, H3O+, H2SO4, HNO3, and HClO4. Now, I'm going to tell you right now, in organic chemistry, you pretty much never have this guy as a leaving group. You don't really have nitrate as a leaving group that much, but the other ones you absolutely do. Okay, so basically what number 1 is saying is that something like, iodine, I, is a really good leaving group. Bromine is a really good leaving group. Chlorine is a really good leaving group. Water, essentially positively charged oxygen, is a good leaving group. And SO4H is a good leaving group. Okay, so all of these are good leaving groups, right? Iodine, bromine, chlorine, water, sulfate, all of those are good leaving groups because they're the conjugate bases of strong acids. Okay, right? And if it confuses you why that makes something a good leaving group, right? So remember, if I have an SN2 reaction, I can draw that attacking into that sigma star orbital, and then that leaving group leaving. When the leaving group leaves, I get I minus. And if it confuses you why or how you would know that I minus is stable, well, if you know that HI is a strong acid, the definition of a strong acid is something that will just immediately ionize in solution to form H plus and whatever the conjugate base is minus. And if you know that HI is a strong acid, then you know for a fact that it stays ionized, right? I minus has to be stable, because if I minus wasn't stable, then this I minus would just immediately go ahead and attack the H plus to form HI again. But it doesn't. HI is a strong acid because if you dissolve HI in water, it will completely stay as I minus and H plus. Right? The I minus is perfectly happy just being fine on its own. It doesn't need to be buddy-buddy with the H plus. Okay? So that's why this rule number 1 is an actual rule. Okay? So a leaving group is the conjugate base of a strong acid. The other kind of leaving group that you can have is anything that is formally positive. Okay. So anything that is formally positive. And that should make sense to you, because obviously if something is formally positive, so if something is formally positive, then it's going to want to leave, because if it leaves, it exchanges a sigma bond for a lone pair, which is going to get rid of that formal positive charge, right? So for example, if I have a nucleophile, right, so the nitrogen is formally positive here. If the nucleophile attacks this H, and then that sigma bond goes there, obviously the OH minus is now H2O, but the nitrogen is now only has 3 bonds, which is what nitrogen wants, and a lone pair, right? So anything that's formally positive is therefore going to be a good leaving group, right? So if I have a molecule, so we already know that, you know, bromine in that molecule is a good leaving group. But in here, that nitrogen would also now be a good leaving group, okay? For the same reason, water is a good leaving group. Water is also a good leaving group because it's the conjugate base of a strong acid, but even if you didn't know that, you would see that it's positively charged, and therefore it's going to be a good leaving group. Technically, right, we know that oxygen is going to be formally positive if it has 3 bonds, so oxygen with 3 bonds, period, is going to be a good leaving group, right? All of these would be examples of good leaving groups. Any formally positive thing is going to be an example of a good leaving group. And the final thing that is an example of a good leaving group, and this is sort of a very, very niche example, but I'm pretty sure you guys are learning about it already, is an atom that is strained, okay? And the reason that this is going to be a good leaving group is because if something can leave, so an atom that is strained, and usually this is going to involve ring strain. So the classic example of this is the oxygen atom of an epoxide. Okay, so the bond angles of an epoxide, it's an equilateral triangle, so the bond angles are 60 degrees. If you look at the hybridization of oxygen in an epoxide, you would see that it has 1, 2, 3, 4 domains. That means that the oxygen is sp3 hybridized. Now, one thing that I didn't talk about in this video, but hopefully you remember from Gen Chem, is that if something is sp3 hybridized, the ideal bond angles, so the ideal bond angle for an sp3 hybridized thing is 109.5. So if this oxygen wants to be 109.5 degrees bonded, and it's 60 degrees, that oxygen is really, really, really not super thrilled. Okay, that oxygen is really unstable. And so normally, neutral oxygen would not be a good leaving group, but because there's so much strain, the oxygen of an epoxide is actually a good leaving group, and if I have a strong enough nucleophile, like OH-, I can in fact cause that bond to break, and I can actually get that kind of reaction right there. Okay? So those are the three, essentially the only 3 ways. So again, really quickly, leaving groups. Okay? So the conjugate bases of the strong acids. So basically all of the halogens minus fluoride. Alright. So they can either be those, they can be anything that is formally positive, so a formal positive atom, okay, or they can be an atom that is strained in a ring. Those are all examples of good leaving groups. And again, I almost didn't even want to write this last one because it's rare. It's pretty much you're only really ever going to see it when you're talking about epoxides. So it's really just these 2 that I want you guys to focus on. Okay, so last but certainly not least, we can talk about electrophiles. So how in the world do you identify what an electrophile is? Okay, it's very, very easy. Step 1, electrophile is anything. Well, actually, you know what? I'm gonna do a different one first. Step 1 of an electrophile is a carbocation. Okay, that's pretty easy. Obviously, a carbocation is going to want electrons because it is electron deficient. Okay, it's a carbocation. Okay, the second version of an electrophile, so it is anything, okay, and it is anything attached to a leaving group. And hopefully you guys now realize that's why I did leaving group before I did electrophile. So anything attached to a leaving group is electrophilic. And this is very important. It's not the leaving group itself. Leaving groups are not electrophilic. It's the thing attached to the leaving group, right? So, for example, right, this carbon right here is electrophilic. This carbon right here is electrophilic, right? Because they are the carbons that are connected to the leaving group, okay? If I have a molecule of H3O plus, okay, right, all of these hydrogens are electrophilic because they're connected to the formally positive oxygen, right? They're connected to the leaving group, right? So electrophile, it's either a carbocation, it's the thing connected to a leaving group, okay, or it is a carbon oxygen or carbon nitrogen pi bond. So just like we said that carbon-carbon pi bonds were nucleophilic, it turns out carbon-oxygen or carbon-nitrogen pi bonds are actually electrophilic. Alright, so with oxygen, it's really only ever going to be a double bond, but with nitrogen, you can have C double bond N or you can have C triple bond N. Both of those are obviously going to involve pi bonds, so all three of these cases are going to be electrophilic. Alright? And I think that's actually all of the examples that I can think of for things that are electrophilic. Okay, so that pretty much wraps up all that I wanted to say about this. I guess basically the only thing is, now that we've talked about, sort of how to identify a nucleophile, an electrophile, a leaving group, we've talked about sort of how to think about nucleophiles and electrophiles. When you think about a nucleophile, you should think about a very, very high energy molecular orbital. You should think about a HOMO. When you think about electrophiles, you really should be thinking about the LUMO. Okay, that's what an electrophile is, all right? We've talked about hybridization. We've talked about all of that. So those concepts that I talked about, and I'm sorry this video is so long. I didn't think it would be this long. I will make another video because at this point I think I'm running out of time. I don't want to keep going. But these are kind of like basic concepts that I really want you guys to be good at, and I really want you guys to get the hang of it. Alright, so I'm not going to talk. This video is pretty much over. The next video that I make is actually going to be going into what you guys are learning right now, which is chapter 12. And I'm just going to go over, sort of how to do or how to think about reactions with alcohols and epoxides and ethers, which I think is what chapter 12 is on, especially in the context of molecular orbitals and homos and lumos and nucleophiles and electrophiles and mechanistic chemistry and all of that stuff. So hopefully you guys liked this video. If you didn't like it, please actually tell me why so that I can change it, so that I'm not continuously making videos that you guys hate. At this point, it's actually Wednesday morning. It's 6:10 a.m. Holy fuck. Yeah, so I'll see you tomorrow, and hopefully you guys have a great day. Ye fucking haw. I'll see you soon.